Okay, now we're ready to talk about Bayes' theorem, which, as you will see, is a application of conditional probability, and in particular also the law of total probability. Bayes' theorem, also called Bayes' rule, okay, again, as we start to read the definition, you notice we are looking at a partition, okay, A1 to AN, they're disjoint, and their union is the sample space, okay? So what this is saying here is that, again, just like what we defined earlier, A1 through AN, it's a partition of the sample space S. Okay? Moreover, they have this any event of probability of any event is positive, okay? And they're also looking at PB, okay, greater than 0. Okay, so this is the setup. And now we're ready to talk about the Bayes' theorem, which, if you look at it, might look a little bit confusing, but I'm going to break it down to you step by step, so it becomes more easier to understand. Okay, so notice here, okay, we are, instead of looking at PB given any of the AI, like what we had known before from the law of total probability, we're actually looking at the flipped, okay, the flipped version of the conditional probability that we have seen before. Okay, so what this is telling us is that, yes, we do have a partition of A1 through AN of the sample space, okay, and we also have an event, okay, a possible event with probability greater than 0. Then Bayes' theorem is actually helping us to answer the question of the reversed conditional probability of AI given B. Okay, the way to get to that, okay, as you can see here, is that, well, first of all, this nevertheless is a conditional probability, right? So we know that there should be AI and B, that's the joint, right, over B. Okay. So, but in order to get it, well, we know that the joint can also always be written as the product of the conditional and the marginal, which is the other way around, as you can see it. Suppose we know PA, okay, it's a partition, so it's likely that we do know the probability of AI. And then it's also likely that we also know the condition of B given AI, okay? And the bottom, well, if you remember from the law of total probability, well, this is the law of total probability to get PB. Okay, so that's the breakdown of the Bayes rule. And I just want to mention that it's not that different, okay, from what we have seen with the law of total probability and the conditional probability. Bayes rule is useful when we're trying to answer the reversed conditional probability question. Okay, and the breakdown, as we can see, we start off with the conditional probability definition of this, okay, and the top is the joint, the bottom is the marginal, and the marginal, PB, is obtained through the law of total probability, whereas the joint, AI and B, is, again, obtained through the multiplication rule. Okay. So this, later we're going to put into practice, and I will just mention that a lot of times we consider or call probability of any of the AI is the prior probability, okay, meaning that, well, it is the marginal that without knowing anything about B, I might have certain probability for any of the AI. And then later, once I know some B, okay, which is helping me to understand my AI a little bit better, and we call it a posterior probability. Okay, so the prior is talking about prior to knowing about B. And then once we know B, so the marginal becomes a conditional here, okay? Conditional on knowing B, I have some updated understanding of AI, so we call it as a posterior probability, okay? A lot of times you will see in the examples coming up will be that A, maybe some of our hypotheses, those AIs, we might have different hypotheses and then assign different probability to each of them. And then B is what we call, like, we collect some data, we observe some data. So before observing any data, we might have some understanding or guesses about each of the AI. And then that's prior. And after we observe some data, we might have an updated belief about each of the hypotheses now. Okay. So without further ado, let me show you an example first. Let's just say that's a student. All of us only has 3 possible majors. Okay, math, music, and econ. Okay, and what we are supposing further is that there are no double majors. Okay, and we have a partition here, as you can see, 25% of the students are in math, 55 are in music, and the rest is in econ. Okay, so no double majors, meaning that it's they're disjoint, and also there are only 3 possible majors, so it's a partition. Kemper's folklore say that 90% of the math major wants to go on dates, compared with 50% of music and 10% of econ. Okay, so this, as we know, some numbers here, so let's think carefully whether this are conditional probability or any marginal probability or joint probability. Okay, all right, let's just say your roommate meets someone at an event and gets a date. What is the probability that she's dating a math major? Okay, so we have a few numbers here. Okay, as we have seen in the previous examples, we really need to set it up correctly before we can actually use any kind of result that we have covered. So let me just phrase it for you that the 3 majors, as we know, define a partition. Okay, and we do know the marginal probability of each of them, 25%, 55%, and then the remaining, I guess in this case, 20%. And then the Kemper's folklore actually gives us the conditional probability of, if we define A1, A2, A3 as the majors, and then B is hoping to get on dates. Okay, so B, let's just say the conditional probability of B given A1, suppose A1 is math major, that will be 90%, okay? Because the Kemper's folklore said that 90% of the math majors want to go on dates, okay? So if we now go back to the question itself, okay? Your roommate meets someone at an event and gets a date, okay? So this is, gets a date already, okay? That's being conditioned, okay? What is the probability that she's dating a math major? So if I try to phrase it in the way that we've been doing this probability statement, the point, and we know that the Bayes rule is able to help us to find the reverse conditional probability to get AI given B. Okay, so specifically if we define A1 to be math major, so we might be answering the question of probability of A1 given B. Okay, so again, don't forget B is the marginal probability of getting a date, okay? And we can use the law of total probability to get that inside of the Bayes rule, so remember. And we do have the marginal of each of the A's, okay? A1, A2, A3 from this partition, okay? And we get the conditional of B given all of the AI in the second bullet point. All right, so that's the question, okay? And here we repeat the example just one more time with the numbers so we get it right, okay? And the question now becomes, find the probability of math given getting a date, okay? So we define A1, A2, A3, okay? They are a partition and we know the marginal probabilities. We define B to be date. So in order to calculate P A1 given B, we're gonna use the Bayes theorem. The Bayes theorem goes this way, as we know. P probability of A1 given B, okay, is the joint of A1 and B, which is broken into the product of B given A1 and the marginal of A1. And then in the denominator, we use the law of total probability, which we list all of them one by one. So we have 3 different A's, okay? Each of them, we're doing the product of the conditional and the marginal. And then when we sum them up, given the law of total probability, we're getting the marginal of PB. Okay. All right. So given all the information that we have known here, you will see that we will get a probability of 43, which is the conditional probability that if someone gets a date, what's the chance that she is dating a math major? Okay. So again, there are, like I said, multiple numbers going on, okay? And we do need to clearly identify which one is which, okay? We know that for a Bayes rule example, which one is which depends on which one is the marginal, right? Which one is the conditional, and then from there we can get the joint, and then eventually need to define your problem carefully in order to do anything about it. Okay, that's all.